Now that we've taken a closer look at number systems and their binary operations, we're going to learn a little bit about being careful about precisely defining arithmetic operations on our number systems. So we're first going to introduce the idea of using the number systems that we already understand to define arithmetic on extensions of those number systems. And the example we're going to look at in that way is going to be taking what we know about addition, subtraction, and multiplication of natural numbers and using those to define those operations on the integers. All right, so in general, if we want to define what a number system is, and by number system, what I'm really talking about here is what we're later going to call a ring, we need to do the following. So we first have to say, what are the elements in the number system? And then we have to define how to add two elements of the number system. We have to define how to multiply two elements of the number system so that people understand what those binary operations are. And those three items together define exactly what the number system is. They have elements, they have an addition binary operation, they have a multiplication binary operation. So here's the deal though. Whenever we construct something, we have to assume that something exists because you can't just build something from nothing. So when we're talking mathematical logic, all we get to assume is that we have sets. That's a fun thing to do. If by fun it means you take a lot of effort to construct little things, I enjoy it, but you may or you may not. So we have axioms to define what sets is, and that's our starting point. We have sets. And then we build everything else in mathematics from sets. Now, in Math 350, we're not getting down all the way to ground level with sets. We're actually starting with integers, and we build from there, right? Well, except we don't do that with real numbers. Real numbers those are weird. You're going to have to wait till Math 408 to deal with those. Where we're going to start in this video, however, is actually where we started back in elementary school. We're going to start with natural numbers. So the question is, okay, so how would we define our number systems if we had to start from natural numbers? And believe it or not, starting with natural numbers, if we went step by step, we can go all the way from natural numbers to precisely defining what the real numbers is. I'm not going to go that far. I'm just going to go to integers here. But when we say, what do we know about natural numbers? Well, it's all the things you knew when you were in elementary school. We know how to add natural numbers together. We know how to subtract natural numbers as long as we're taking bigger numbers and subtracting smaller numbers from them. We know how to subtract 10 minus 4. We do not know how to subtract 4 minus 10. So if anything demands that we subtract 4 minus 10, that's something that's not allowed in our definition. And of course, we know what multiplication is. So assuming we know addition, appropriate subtractions, and in natural numbers, and multiplication, can we then construct the integers? Well, the answer is yes, and that's what we're going to do right now. So we're going to define them assuming all we understand is natural numbers. Now, this may include constructing other numbers based upon those natural numbers. But again, we can do that because we can work with sets. So here's what our starting point is. We know what the natural numbers are. There's just the counting numbers. 1, 2, 3, 4, 5, etc. So we're going to use those to defend the elements of z. Well, for the elements of z, of course, we're going to include the natural numbers. We're also going to toss in a new element we're going to call 0. That's our additive identity, right? And then, other than that, we have to toss in the negative integers, which all those are numbers that correspond to the elements of the natural numbers, but we're just considering them to be the additive inverses. So they're all the numbers that look like negative n, where n is a natural number. So we have a natural number 5, we have a new element that we toss in, negative 5. And what defines that? Well, we don't know what defines it yet. Right now it's just a symbol, a 5 with a negative symbol in front of it. We have to wait to determine what it means in terms of addition and multiplication. All right, so now we've told you what all the elements of the integers are. They're all the natural numbers, a new element 0, and some new elements that are the natural numbers with a negative symbol in front of them. So for addition, well, I got to tell you what addition is for all possible cases for A and B. So we're going to let A be and B and Z, which means that A or B could be natural numbers, they could be zero, they could be the additive inverses of natural numbers. So the question is, what is A plus B? And the way we're going to define it is going to depend on what kind of numbers A and B are. So for instance, in the case that A and B are both natural numbers, we just say, well, A plus B is exactly what it was in the natural numbers. Again, we're assuming that we can add in the natural numbers. So saying A plus B in the natural numbers is something that we already know, so we can precisely define what A plus B is in the integers. So now the new ones are going to be when one or both of them is 0, one or both of them is negative, right? So if A is equal to 0, well, let's see. A plus B is going to be equal to B, right? Because 0 plus B should be equal to B. It's an additive identity. And again, I don't have to specify what kind of number B is in this case because we're defining that for every single integer B. If B equals 0, we're going to do this similar thing. A plus B is equal to A because, again, our reason is because it's the additive identity. We can define it to be whatever we want. We just want to define it in a reasonable way. This defines it precisely. All right, so now what happens when we take a natural number and add to it a negative number? And what does a negative number mean? It means B is equal to negative n, where n is a natural number. So we took one of our natural numbers, put a symbol negative in front of it. That's one of our new elements. Well then, how do we do A plus B? Well, it's gonna be tricky because it depends on whether A is bigger than n, equal to n, or smaller than n, right? I mean, if A is bigger than n, then adding A plus B is just taking our A and then subtracting the natural number part of B, right? Ignoring the negative part on the negative n, and then just subtracting that number, right? If I do 6 plus negative 4, I can think of that as 6 minus 4. 6 minus 4 is something I understand because that's subtraction in the natural numbers. So A minus n is something I understand because A is a bigger number than n, so A minus n actually makes sense. Now, if A is equal to n, of course, if A is equal to n, that means it's A plus negative A, right? We want that to be 0 because they're additive inverses of each other. Now, if A is less than n, I can't just say A minus n because that doesn't make sense in the natural numbers. I need bigger numbers that are minus smaller numbers. But I also know that if A is less than n minus A is a number that makes sense to me, right? And what I do is n minus A gives me a natural number, and I just take the additive inverse of that natural number, right? If I'm taking 4 plus negative 6, what I'm doing is I'm taking 6 minus 4 is 2, taking the additive inverse, negative 2. Now I'm going to go through the same process if A is a negative number. In other words, A is equal to negative n, where n is a natural number, and where B is a positive number. So B equals a natural number. So, and once again, if B is bigger than n, then A plus B is just going to be B minus n, right? I just take B and subtract the absolute value of A, if we want to think about it that way. If B is equal to n, of course, we want A plus B to equal 0. They're additive inverses of one another. If B is less than n, I can't do n minus B, but I can't do B minus n like I could in the first bullet point. But I can do n minus B and then take its additive inverse. And then if they are both negative, actually that's going to be the easy one, because if I have like negative 3 plus negative 5, I take the 3 plus 5 is equal to 8 and I take its additive inverse. I'm going to do the same thing here. A plus B is I take m plus n, then take its additive inverse. And that takes care of all the possible ways that I can add two integers together. And again, all I have to know in order to know how to do all those things is I have to know how addition and subtraction work in the natural numbers, and I have to understand how the negative numbers and 0 works symbolically. All right, so now let's look at multiplication. That's actually going to be even a little bit easier especially now that we've done addition. So we're going to let A and B be integers. What is A times B? Well, if A and B are both natural numbers, A times B is exactly what it is in the natural numbers, right? We're not changing the multiplication in that case. If A equals 0, A times B is going to always be 0. Anytime we multiply by 0, we get 0. And again, no matter what B is, that should always be 0. If B is 0, again, multiplying by 0 gives us 0. if A is a positive number, if A is a natural number, if B is a negative number, in other words, negative n, where n is a natural number, well, let me see, a positive times a negative equals a negative. Then we take the A times B is going to be A times n, but then we put a negative in front of it. If A is the additive inverse of one of the natural numbers and B is a natural number, then A times B is just going to be, we do n times B and take its additive inverse. And if they both happen to be negative numbers, A is negative m, B is negative m, where m and n are both natural numbers, then when we multiply those together, the negatives are going to cancel each other out, and it's m times n. And again, if you look at all those bullet points, as long as you know how multiplication works in the natural numbers, you can understand exactly what all those binary operations mean. All right, so now I'll give you a chance to work on some other number systems. It's called Number System Examples, and that's the name of the PDF file included with the video.